how do you build the best model, right? We have some of them, we have better ones, we continue to build them. That's not enough.
What happens when a precision health researcher reimagines cancer screening from the ground up and then builds the AI to make it possible? In this episode of Neural Compass, How is ML Improving Cancer Diagnosis?, Dr. Adam Yala, professor at both UC Berkeley and UCSF, joins me for a deep dive into the future of personalized medicine. We cover everything from why traditional cancer screening is too coarse and how AI can change that, to building risk prediction models that outperform today's gold standards. We talk about the challenges and promises of applying ML in real clinical workflows and what adaptive trials, synthetic data, and LLM safety have in common. Enjoy the conversation. Hi, everybody, and welcome to the Jimini Health Podcast. I'm Mark Jacobstein, the co-founder and president of Jimini Health. In our conversations, we try to explore the frontiers of AI, mental and behavioral health, and any interesting ancillary topics from precision medicine to genomics. I am really excited today to be speaking with Dr. Adam Yala, who is an assistant professor of computational precision health and EECS at both UC Berkeley and at UCSF. We'll talk a little bit about how he manages that. He has focused his research on everything from developing ML methods for personalized medicine and also translating those to clinical care, worked in oncology, predicting future cancer risk, and designing personalized screening policies, a really interesting topic that we're going to get into. Did his training at MIT sort of all the way through undergrad and then graduate training with the incomparable Regina Barzilai, who is responsible for our introduction. Really excited to have you here today, Adam. Welcome.
Thanks so much for having me.
Yeah. So I thought the first thing it'd be really interesting to talk about, in part because it's near and dear to my heart from my time at Guardant Health, is the work you've been doing on predicting future cancer risk and designing personalized screening policies. And maybe I'll start with sort of my framing of the challenge, and then I'd love to hear about the work that you've done, both your sort of seminal paper, Rethinking Risk Modeling with ML, and then subsequent work that you've done thereafter. The way I think about this is catching cancer early, particularly with certain cancer types, is, of course, incredibly important. This is why we do cancer screening with everything from mammography and breast cancer to colonoscopies and other newer modalities in colorectal cancer. The challenge is that the AUC is not perfect for any of the modalities. We have false positives and we have false negatives. And in most situations, the prevalence is relatively low. And this leads to all sorts of challenges for how we think about testing, because if you test and you find things that aren't real and you go and cut somebody open, you can really hurt them. It costs a lot of money. You cause great fear. On the other hand, if your sensitivity isn't high enough and you don't catch things early, people die from cancer. And it's a real conundrum. And the way we've dealt with this historically is we have had population level models for how often people are likely to get something. And that, along with the sensitivity and specificity of the testing modalities, drives how we think about when people should get tested, how they should get tested, how often they should get tested. And the problem is it's really coarse. It's a really coarse modality. So that's my sort of framing on the issue. You've done a lot of work to, I think, help build better modalities. So maybe I'll stop there. If you want to talk through the work that you did with this initial paper and then sort of the work that you're doing now, that would be great.
Yeah. So I'll just add something to that, to the context before diving into the kind of first set of models that we built. I think it's commonly appreciated that like a diagnostic modality like mammography has a known specificity and sensitivity. What's less appreciated is that our mammography guideline has a sensitivity and specificity. Like the thing that sets the prevalence is actually another algorithm that we're applying in society to say who gets a mammogram in the first place. And so every time you see someone who gets, let's say, breast cancer at age 35, that's a false negative by the mammography guideline because they could have benefited from a mammogram. They just were never eligible for it.
Right.
And if you have cases like pancreatic cancer, which are much more rare, we have no guidelines, right? Like it's too rare. We have the occasional pocket here and there for folks with particular mutations, but by and large, the vast majority of cancers are caught completely by accident.
Right.
And so like the big problem is like, how do you even pick that guideline as an algorithm design problem?
My father's kidney cancer was discovered with a scan that was happening because he had sepsis. It's a classic story of some other scan was happening as the only reason that they caught his cancer. And maybe just to lean in on your point about mammography, there are very specific populations of people who get more testing and different testing. So if you know you're BRCA positive, for example, you're going to have a very different testing modality for breast cancer. But that's extremely rare compared to, and almost everybody else gets thrown into sort of the same bucket.
Yeah, exactly. So I think there's a big opportunity to say, like, there are exceptions, or like the BA circulation is a great one where we know enough to do something really great and much better than the normal testing regime. But for too many people, it comes as a complete surprise. You should have no idea.
Right.
And if we had that kind of fine-grained things, you should be able to both reduce the absolute rate of advanced cancer while making overall care cheaper. Because a bunch of people who get, what's the prevalence of regular screening mammography? It's 6 in 1,000. Right? The vast majority of those mammograms won't catch anything. And it's not because we believe that the negative mammograms are useful in their own right. It just, our guideline classifier is so coarse that we don't know how to modulate this regime to kind of get both better and more efficient.
It's very interesting because when you deal with, like, for example, the advocacy community, generally speaking, people simply want more testing, younger, et cetera, because they want fewer people to die from cancer, which is a noble goal. What people fail to appreciate is that testing, it's not just that testing costs money. It costs time, it takes days, and a false positive is terrifying, and it also can lead to things like unnecessary surgeries, unnecessary biopsies. There's real harm done every time we test somebody who doesn't need to be tested. And this is one of the things that people generally don't think about.
So I think it's like, oftentimes the debate is like, there's a frontier of, like, Pareto trade-offs, and we're arguing about where we are in that frontier. And what we're trying to build is just, how do you make that frontier better and empower people to make those choices better? Because it's when you don't know the risk of something going wrong, you don't know the benefit of the thing. It's very hard to have it informed, like, okay, well, here's the trade-off that I want, and I'm empowered to make a decision. That's because information is lacking. Yeah. And like the main classifier that we use in many of these regimes is just like age. Which, like, this univariate model that kind of guides our guidelines. People say biennial, annual, start this year or not. And as long as we stay within that regime, there's only so much we can do. And in many diseases, it's just not enough. Like, age is not powerful enough to tell who should get pancreatic cancer.
Right.
So, like, big picture vision, like we've been trying to get to for a long time, is how to use everything we know about patients, like everything, to understand.
Personalized screening, I think, is
exactly.
Yeah.
But like more generally, like, how do you look at everything that we actually have available, which is gigabytes and gigabytes per person, and say who has what now, who's going to get what, and what we should be doing about it.
Yeah, and it seems like there's sort of like a master algorithm, which is some sort of like everything we know about you and what that means for risk prediction times the value of an intervention. So one of the things people don't talk a lot about is, of course, discovering cancer early, generally speaking, useful. More useful in certain cancers than it is in other cancers, and likelihood of it actually changing the outcome changes depending on the type of cancer. And of course, there's also the harm and cost of the intervention, which is also differs from testing modality to testing modality. A colonoscopy is a lot more expensive and a lot more invasive than certain other types of testing modalities as a for instance, but it's also wildly effective and incredibly important. And our deaths from CRC have gone way down because of colonoscopy. Anyways, so tell me about, I love this notion of sort of personalized screening. Tell me about the work that you did. And I guess it started in Sweden, it was a study in Sweden and sort of extended from there.
Yeah, so this was back in my PhD. We had this collaboration with MGH, and we built image-based risk models to understand who's going to get breast cancer. So this field has like a long history. People have been thinking about this in some way or another since like at least the late 60s. People like looked at our breast and said, okay, something about what the thing looks like might tell me something. And people eventually formalize this as breast density. For any people listening who've gone through mammograms, you have this like formal letter that's mandatory sent out that the breast is dense or non-dense. And that is like a nearly 60-year saga of trying to take something that people have been eyeballing and formalizing into a concept that's not part of like standard reporting. It is a risk marker, like it passes a hypothesis test. Like
it means something.
It means something. It's just not very refined. And like if you step back and go to other industries, like we don't do ads that way, right? Like we kind of look at like a very personalized, what can we figure out from this individual profile to say what's going to happen. And we don't just like eyeball people at a very coarse scale from the 60s and then keep that static over time. So what we did in that first work, so again, premise, we know something's inside the image. People have been eyeballing it for a long time. What can we learn from directly, and how much can we beat the existing population-based models by just doing like you have 4 views of mammogram, look from pixels directly to understand cancer risk over the future. So we built this with MGH. We showed that we could do quite a bit better. There's a little more technical innovations I can go into if people care. But like if it's just MGH, it could be a fluke. So we spent a lot of time like, okay, well, like let's just actually work at scale.
Right.
So we spent a lot of time reaching out to potential collaborators, and some really now great friends have, took us on and like let me travel to Sweden so I can start collaborating with Frederick Strand to externally validate the model there. I visited Gigan Lin in Taiwan, and like slowly now we're at something like 40 hospitals across 14
Amazing.
countries, something like that have not tested the model. And across these different experiences, we know the thing is robust and reliable and gives you a real boost over the standard of care.
And the thing is looking at scans, it's looking across the entire EMR. What are the data types that are informing the model?
Yeah, let's tell you where we are now and what has been historically intractable, kind of where we're going.
Right.
So where we are now, we have a similar model in lung cancer and like some things we're building in pancreatic and prostate. You have a single scan. So you have the mammogram today, and the objective is who's going to get cancer within the next 5 years. So I'm predicting both cancer today, within a year, within 2, 3, 4, 5. The equivalent of this lung cancer is like you take an LDCT, lung cancer across 6 years.
And we all know what the predictive power of that initial LDCT is. It's sort of famously terrible in terms of the actual predictive power, but that's a longer conversation.
Yeah, it's
with older technologies. I would imagine at modern ML applied to those same LDCTs, I suspect we can pull so much more signal out than the initial LDCT study from however many years ago when the USPSTF first said, yes, if you're a 30 plus pack year smoker, you should probably kind of sort of maybe get this screening because it just barely gets over the threshold of utility. My suspicion is that modern ML applied to those exact same scans, not to mention the scanning technology gets better, is probably much, much, much better.
Well, these are really like orthogonal problems. Like one is like, can we do better on the existing technology? Like, I mean, for sure, I mean, slice thickness now on these CTs is like less than half what it used to be. Right. So there's a lot more resolution to be had. Even humans on current LDCTs are better than humans on prior LDCTs.
Right.
Let alone like models that we can extract out. But for the use case of who's going to get it and how do you change frequency, like the baseline is just pack years, and you can do much better than that.
Right. Well, it's again, to your point, it always struck me as like literally the one thing, they're like 30 plus pack years of smoking. So you could smoke 3 packs a day for 10 years or 1 pack a day for 30 years, or it didn't matter how long you'd quit for, it didn't matter other risk factors. And of course, it was still better than nothing for sure, but very, very, very coarse.
Yeah, I mean, it's a testament of like the tools that we had. And if you look at like, that was built off of the Polko kind of clinical trial data sets. You can kind of build, like it's actually a homework I do in like the class that I teach. Like you kind of reproduce the endless criteria by like playing with it. And like, if you try incorporating like pack years plus quit duration and other kind of markers of course intensity off these questionnaires, you get marginally better, but it's not that much better. Like you need to go quite a bit deeper to actually be able to see a big boost. Right. And looking at the imaging directly teaches you stuff through that kind of mechanism. Now everything is one scan. There's a lot, like that's the megabyte regime. So what have we done? Like before we had bits, we skipped kilobytes, we went straight to megabytes. But there's a lot, like that's not patient care, right? You have actually that over time. You have that plus the full EMR and other incidental things you've had over time.
Let alone like, family history, advanced omics, whatever else.
You can start going to like what happened to your to your people, both your community and out over time. And that, as a big picture, has been historically intractable because the kind of inputs that you have, like in LLM regime, we say like this big LLM can take 100,000 tokens. We need to have tens of billions of tokens. And like making modeling efficient in that regime, in the data scale that we have very deep data per person, but not very many people comparatively, is quite a bit harder. And so that has like a big swath of technical challenges that we focus on now.
Well, it also strikes me you have a lot of different challenges. I mean, I think maybe the dream is if we had all the data and you could apply your ML models across them, you would have an enormous amount of signal, both in terms of likelihood of risk and hence the type of screening modality that you should incorporate, and then what your interpretation of said screening modality would be. The problem is you have both a population scale data problem. There aren't that many patients with whom we have this complete data, but then also accessing the data. I spent a lot of time when I was at Guardant and some other projects, like accessing the data, even when somebody's inside a single health system. Like I happen to be at Kaiser and all my stuff is at Kaiser. It's still not that easy to go get all the data, let alone what actually happens in oncology care, where people are often seen initially by a primary care physician, and then there is a pathologist, there is a community oncologist. Maybe when the disease is later metastatic, they get kicked up to tertiary care center, which is a completely different hospital. And going and pulling all of that together is really challenging. And so, first of all, kudos to like getting 40 organizations on board. That's probably as much work as the actual ML. I'm curious, where are you today in terms of sort of how much signal you feel like you're able to pull out, the value of the algorithms today, and where do you think, like asymptotically, how good does this get?
Yeah. So, I mean, right now we're running some multi-site clinical trials. So we started off running a trial back in 22 with colleagues at UMass Memorial Hospital. The premise there was like MRI is the kind of next layer of screening over mammography. That's the most sensitive modality we have to date. Let's run one where we're using the AI-based model called Mirai, it's the mammography-based one, to select who should get an MRI. That's accruing patients now. That's supported by BCRF. And now we're adding 3 new sites, including UCSF, UCSD, New Chicago, and we'll continue enrolling patients for the next 2 years or so before being able to read out results. So like, there's really kind of 3 types of challenges in the space. One of them is like, how do you build the best model, right? We have some of them, we have better ones, we continue to build them. There's an asymptotic picture there as we get more flexible tools to say, if you have variable amounts of information, how do you like better predictive power? That's not enough, right? Because you just know like a better risk, or you need to do something about it.
Right.
And like, there's a causal story here, because like the data will never tell you, well, if this person had an MRI 6 months before this happened, what would have happened? You don't know. You make some assumptions, you build some control algorithms. That's kind of like this, like, how do you say, here's the personal screen policies I think would have helped? But then you still need to like, one, even make them is like its own research agenda in itself. And there's a lot of interesting challenges there, because like you obviously need to have foresight to have control.
Yeah.
But once you have foresight, control is not trivial. And there's a lot to explore there. There's like, and there's many different kinds of modalities, like in even just breast cancer, there's like contrast enhanced mammo, there's MR. If you get a negative MR, does it mean you could stop? How do you condition what you saw there? There's a bunch of stuff there. And even when you have that, how do you do trials that make sense? Because no matter what, like one thing I know for sure is going to happen with this trial that we're running now is by the time it's done, we'll have better algorithms and better control.
I'm so glad you brought this up, because this is one of the great frustrations. So, you know, again, while I was at Guardant, I spent a lot of time thinking about the USPSTF, and because Guardant was working, its primary technology at the time was ctDNA assays that allowed you to go on the right therapeutic modality if you had metastatic disease. But the dream was, and where Guardant is today, it was to work on screening modalities where with a blood draw and looking at circulating tumor DNA and other sort of omics markers in the blood, we could start to do screening for all sorts of different tumor types. There are many, many, many challenges, including, to your point, like whatever you started with is tomorrow is already behind. But when you are running a clinical trial, right, you're not allowed to go post hoc, update the algorithms. I mean,
but I actually think even that has space for, it's because we haven't had the method to do that in a rigorous way. And that's like the third bucket of research that we're working on, because like, and like drugs, drug A, drug B, they give these completely different things. Like there's no way to recycle data from one to the other.
Right.
One thing that's common across the broad class of AI algorithms that we're exploring is they are not care, they allocate care. And if you get an MRI because model A or model B told you to at the same point in time, it doesn't matter.
Right.
Right. Like given you got the intervention, everything else is the same. And so that means you could actually have adaptive trials where you swap out the model over time, and you're like, you have rigorous sample size calculation, rigorous enrollment criteria, everything just kind of works. So you move away from this kind of one-off trial to continuous platform trials that get cheaper and cheaper.
Yes. And I love that. And the challenge, of course, is you're working inside the health ecosystem, which has, so this means if you're going to do such things with that level of innovation, you have to drag, sometimes kicking and screaming, sometimes not. Everything from like IRBs to the USPSTF, potentially FDA, depending on what you're doing, et cetera. And there's very good people who want to do innovation in all of these places, but you're at the absolute cutting edge of this. And in a field that is, for good reasons and bad, has enormous status quo bias. And so one of the things that will be interesting is for you, I know you work on translational medicine, as you work on like the core research, and then how do we think about actually making this thing happen? Like we've discovered a way to do, better screening and in personalized screening. How do we take a system where even basic screening doesn't happen when it should, even when we find things, people don't do the right things. I mean, not to be a wet blanket, but I still have scars from like, in oncology, something like 44% of metastatic non-small cell lung cancer patients who have an EGFR mutation do not go on osimertinib first. They end up on pembro, which is literally contraindicated. Why? Longer conversation, but this is the sort of thing that like makes the changing of behavior really challenging. All that said, I think that what you're doing is incredibly important. I'm really excited to see the results. And intuitively, this feels like where it should go, right? I mean, we've known since 2017 with the Sebastian Thorn Derm paper that the machines were going to be way better than the people when we looked at things like scans, let alone when you incorporated all this other, multimodal information. And I'm really excited to see kind of where this all lands. When do you expect to have readouts?
So on the trial, I expect to have readouts in about 2 years from today. But you mentioned there's so many challenges. Even like solving this one particular screening challenge has like better model, better control, better like evidence generation, haranguing the whole evidence world to kind of get around it. And I think something that I see like is common in this space is like you just can't go small. If we were able to roll this out at scale, and let's say that the trials work out, making them financially sustainable to have this kind of like, because now it's not just like you look up a website. So you need to run an algorithm. The algorithm should be updated and maintained. It has regulatory cost.
Right.
Having that be financially self-sustaining is its own can of worms. So there's a separate team of students looking into that because it's non-trivial. Because you don't have things like that and the incentives aren't quite as clear.
Right.
And that will only
and the business of molecular diagnostics or any diagnostics in general is not very good compared to therapeutics for, again, a longer conversation, but sort of an order of magnitude less reimbursement, generally speaking, for the diagnostic piece. Even though, as we know in oncology, the most important thing you can do is find it early and cut it out, right? I mean, by the time I'm applying very expensive drugs in a metastatic setting, things are a whole lot worse.
Yeah. So I think the other thing kind of going that vein is like, even if you catch it early, you're going to have like more consistent actual interpretation, more consistent treatment decisions. And so there's a really like everything is a problem. And if you improve any only one part in isolation, you will get bottlenecked by other things down the line.
Right.
To me, the kind of what gives me hope is that the technical foundation to do all of them better is basically the same. When I think about how to do better trials, this is not a better trial thing for this particular AI model.
Yeah.
The same technique will apply to both the new diagnostic stuff that we're doing and all this personal screening stuff across every modality. They're general tools.
Right.
As you get better building stuff in the breast cancer setting for risk assessment, it's also better at like as a report generation tool to help improve the diagnostic workflow, which usually help make things more consistent. And that's the same kind of thing as in as an input to the broader oncology one, like to make
and I think if you are able to solve, I mean, there's some very general problems too, like how do I get a health system to give me enough data in order to build a predictive algorithm that is useful? If you solve that in a breast cancer setting, you've kind of sort of solved it for lung cancer, colorectal cancer, prostate cancer, pancreatic cancer, et cetera. Not entirely because some of the screening modalities are different, but at least the EMR extraction and access via the health system and an understanding.
Yeah, the basic relationships you have to build to make that possible is the same. And like building a collaboration for one is roughly as easy as getting it for 3 or 4.
Yeah.
And making it work across 4 at the same time with the type of technologies that we have now is simply much easier than any one of them in isolation.
Yeah.
There's a lot of humility that one has to have working in the space because things are infinitely hard in every direction. But I think there is it does not mean that one can't make solid incremental benefit. And the technologies that I think that technology innovation in the space is just giving us bigger and bigger leverage.
Yeah.
Like, it's not my vision that we're going to say my goal for my, next 5-year push is just we're going to roll out breast cancer screening innovations and the trial's going to be done. That's it. That to me is like, we're going to go high volatility. We're going to get like
this is the work of a lifetime. This is the work of a lifetime, I think. And
any one thing it can be, but I think it's the by the nature of knowledge that we're building, you can work on many of them at the same time.
Yeah.
Because the trials are totally independent from each other. And so I'm expecting that we should be both pushing a new type of diagnostic innovations and make the workflow more consistent, improve that part of the workflow, package it up with the screening stuff. Because if you doing both is currently feeling quite easy to doing any one of them in isolation. And so I'm quite optimistic of the leverage that's being built out.
That's fantastic. And it'll be very interesting to see because, as you know, different indications, again, the interventions have very different success rates, et cetera. It's hard to know a priori which one is going to sort of pop as the thing where you can sort of save the most lives or the most qualities in advance. But it's really exciting work. So thank you for that. Shifting gears completely, I want to talk about LLM safety. So I had a chance to read your paper, which is an archive on sort of conformal language methods, and said loosely that the problem, as best I will describe it, you're trying to solve. LLMs hallucinate. That's problematic. It's particularly problematic, of course, for those of us who work in a healthcare setting and for a company like Jimini, which is trying to make safe and effective, clinically rigorous, LLM enhanced therapy for people with anxiety and depression. You can't get these things wrong. It's one thing to like type into ChatGPT, like help me with my research paper, and then to go double check it on your own. Real-time chat with human beings who are struggling. Anyways, you get it. It's a serious problem. And this is over my pay grade technically, but my interpretation of the paper is that you guys have made a very important breakthrough in the ways in which you're able to drive, reasoning models towards accuracy. So talk to me about the methods. And I'd love to have not only a sense of where you think we are in terms of sort of solving for, the alignment problem, the hallucination problems, et cetera, but also where you think we're headed. I mean, the progress obviously has been astonishing. And I'm curious, I know asking you to predict the future is tough, but I'm going to do it anyways.
Yeah, so the focus of that paper, which was led by Adam Fish and Victor Quach, both phenomenal in their own right, is how do you, for a given quality of model, how do you get particular types of uncertainty guarantees for the output that you want, right? And there's many things of flavors of that work. So really there's kind of like two threads of innovation I think are really important. One of them is like how do you improve model quality? So that way, like if you do the uncertainty qualification correctly, the sets get smaller and you kind of get tighter bounds. And that's kind of the third use, that I have no special flavor to add. That's like the RL for reasoning type of stuff and kind of going beyond supervised fine tuning. And there's a lot of things that are very exciting in that direction, including how do you take that outside of just LLMs and also the VLMs in this kind of like broader multimodal world, or given you have a good enough initialization, how do you get further using RL techniques? And that's super exciting.
Yep.
In this paper, we take the other angles, given a current quality of model. If I want to say, you're going to tell me the right thing with minimum probability X, which applies no matter where your model is, or abstain. Then there's a really rich flavor of methods called conformal prediction. And in that setting, the intuition is quite simple. Like if the data is what we call exchangeable, so like what is inside the validation set or what's like the test sets, like it could have been either of them.
Yep.
I can kind of calibrate how well the model is doing in my calibration set. And then be able to kind of like, without any more assumptions than that, say, this has accuracy 95%, whatever my target is, with probability at least 0.99, or whatever that number is. And what that means now is I can say, like, let's say my model is some particular quality. If I just can't guarantee that it's going to hit this performance bar, don't do anything.
Right.
Like, I don't know. And so now you can kind of like have this rigorous kind of QC system. And now you can view like, my model getting better gives me higher coverage.
So can I take something like that and combine it with something like a self-consistency decoding piece? So like ask the model to spit out 3 or 4 or 5 different answers, apply your conformal algorithm where I, in effect, get like I think of it as a version of an AUC, but like my likelihood of this being correct, and essentially multiply those and end up with a very, very high probability, generally speaking, of having a path that I know that I can pursue?
I view this kind of method as kind of the last layer of QC.
Okay.
And so like that way, the output of this, like basically given I give you some proposed solutions, which of them so I'm mixing, there's many different flavors under the same umbrella.
Right.
Like broadly, I'm gonna give you a simpler example off a project we're running right now. We're doing synthetic contrast generation. So as you probably know, breast MR works really well because you're injecting people with gadolinium. People don't want to for many reasons, including it makes the workflow much more slow and complicated. And there's like permanent deposits that people don't want. But actually from the pre-contrast series, I can sometimes generate what the image would look like with the contrast injection.
Okay.
With quite high accuracy. Now the question is when? because I'm not injecting you, right? So I don't want to give you fake contrast.
Right. I only want to give you contrast when I need to.
Exactly. So I need to know that like if I'm showing you the fake contrast, I want to know that this has like the kind of tumor segmentations within a particular margin probability, at least some high number that like we're ethically okay with. And so I want to say if it's not that, don't give it. So now I might say I can only give this boost to only 10% or 15% of the population. As the model gets better, I can keep the same quality bar and grow it to 95.
Right. And depending on your use case, maybe you need it to be 95%, maybe 99, maybe it's 4 nines. It just depends on what your use case is. But your model is going to give me a way of estimating likelihood of
exactly. You want the control accuracy. So you can kind of pick the trade-off based on the use case and like, the regulatory regime. And then you can say, okay, well, if I do my self-consistency thing or I do this kind of like, I'll improve the model in some way, I'm never like I can keep the quality bar and increase my coverage. Right. And this is very useful in this kind of like safety critical kind of regimes where it's better to not say anything than to say something wrong.
Well, and so this is why I brought it up, because specifically, right, at Jimini, what we're trying to build is, AI assisted therapy, where in certain circumstances, the AI is either autonomous or in the future, we hope for it to be autonomous, except when it can't be or shouldn't be, right? And having a sense of, oh no, I'm not quite sure. I'm going to kick this over to a human being because there is an issue. I mean, there are obvious ones in a therapy situation. Somebody describes self-harm or harming somebody else, et cetera. You want a human being involved immediately. But there's much subtler situations than that. And the native instincts of LLMs don't necessarily square with how you actually want to treat a patient in a therapeutic situation. The most obvious example is like LLM sort of complete people's thoughts. Generally speaking, in a therapeutic situation, you don't want to do that. You want ask them to do that themselves, and then perhaps work on cognitive reframing, et cetera. Those things are not like native to an LLM, and you can get partially there with things like, good prompting, but you don't want to get it wrong. And what we've seen in the industry is lots of people using LLMs that are not clinically rigorous, not safe in a therapeutic context in ways that are not safe. And it's unfortunate. It speaks to massive latent demand, which is part of why we help build the business, but it also speaks to like why we feel it's very important to do it right. And techniques like yours, which it sounds like would sort of be like the final layer of QC after all of the other things you do in not just in LLMs, but now in these reasoning models where you might be doing chain of thought and self-consistency decoding and a variety of other things. And then we apply your algorithm. You have a confidence level. If it exceeds what the sort of risk is, then you say it. And if it doesn't, then it gets kicked over to a human being. So this is where we think the future of what I'll say like high value, but potentially high risk LLM communication should head.
Yeah, I think so. I think like there's this kind of like triage system has room to get formalized and at a level that we kind of like the old school production style, like, Six Sigma kind of things. Like we really have, like we expect this % uptime of our data center. Right. And like there's that level of rigor, something that I think is in reach. It's never going to be something that is cheap and trivial, because how do you get that the guarantee is 99.999? Right. Because at least 99.999 times whatever the number of things has been seen to be able to even make that valid determination. And so it's like any other QC process, it's a continuous investment because the model's changing. The way in which self-harm might express itself will also change, right? As culture changes and as like you have like new waves of people coming in.
And as expectations of safety change. I mean, we've seen this in the autonomous vehicle world where we expect self-driving cars to be much safer than human beings in order for us to, every time a full self-driving Tesla kills somebody, it's national news. And it probably should be. And I understand the desire to make the algorithms as good as they possibly can be. They're already safer than human beings, right? I mean, so it's an interesting thing, but for us, for sure, we need this to be it's not just as safe as possible. That's one piece of it, but also the sort of the efficacy and like what does good therapy look like is the kind of thing that requires a heavy QC process, and so we're investing heavily in technologies like yours. So I would take it from your answer that your sense is that this is going to get better and better over time, It never gets perfect because there's no perfect training set, and there's probably no even sort of perfect. No human could do a perfect
There's probably
interpretation.
no perfect like labeling sets. And like if you label stuff, this was a good decision, bad decision, you'll have some inherent disagreements there. Like the upper bound is not perfection.
Right. Just a few sort of fun questions for you. One book or blog or podcast that anyone interested in what's happening inside AI that you would recommend these days? Something that you've consumed recently that you really love?
So this is not just in AI, but I think Eric Topol's Substack. I forget the name of it because I'm often very offline. I'm monastic in my style of work. I go to the mountains. And
Eric's amazing. So we did. I got to do a lot of work with Eric back at Gardent. Actually, he was an advisor and is just such a wonderfully broad and deep thinker. I agree. His Substack is fantastic.
Yeah. I highly recommend. For something that's more imaging specific, there is, I'll have to come back. I would say the strong recommendation, things I actually read on a highly regular basis, is probably Eric Topol, but practically I do a lot of like archive, meta-archive sleuthing. And that's my primary source of news.
Interesting. That's fantastic. And anything else? So that's sort of the general, you should read these blogs or podcasts, but any other sort of branches of research that like you don't have time to be working on yourself because it's finite and there's so many interesting things, but things that you think are particularly interesting and exciting, specifically in the world of like ML meets health tech, because I think there's really particular issues there.
I think there's so many opportunities. So the things I'm actually working on is like, better prediction, better control, all this trial stuff, etc.
Right.
Something that I think is going to be super exciting that I think does not have enough exploration is what kinds of new clinical workflows can you make when you have LLM-based tools in the workflow. So let's say you have a powerful vision language model, and we have some like in the chest X-ray world, right? Right now, the workflow of how someone interacts with the system, you either say, I have maybe full automation. Doesn't really work often enough, but we're getting closer to that in some settings.
Right.
But like right now, the person just looks at the thing, dictates, and it's not trivial. How do you reimagine the workflow given you have these suggestions? Could someone just point at the thing, you get the thing? Does you just ask it questions? How does that work out in oncology when you have like this? How does a multidisciplinary tumor board work when you don't actually have all those people because you're in this kind of lower resource settings? I think there's a huge amount of space of like new interactive workflows that are more.
I love that idea. Because
given the better tools that are like deeply interactive, it's not something that it has a deep amount of exploration now. The tools are a little bit young, right? The tools can continue to get better, but this new kind of like what's a clinician experience, like as I code, it's not what it was 5 years ago, right? It's like way better. What is that in oncology? And I think that is going to be an exciting interactive area. Industry is really uniquely posed.
It's a fascinating point. I used to think about this. You would see you get the molecular tumor board together at an MD Anderson or at a Mass General, and you'd have 10 of the world's great oncologists in the room reviewing a single case. And I used to, it's amazing. Also completely unscalable. And by the way, 80% of the care happens in oncology, for example, in the community with a community oncologist who's highly trained and very smart, but sees maybe one metastatic, colorectal cancer case per year, because a lot of what they do is, they see all tumor types in all different like stages from stage 1 through metastatic, like the whole thing. There's no way they can possibly be expert. And there's no molecular tumor board. So building workflows where you're bringing in sort of the superhuman AI intelligence into the workflow in a way that somebody could actually interact with it is a really hard and interesting problem. I love that. I'll be curious to see how this works out for the next few years.
Yeah, we're seeing the baby versions of that. Like you have things like a Bridge, all these like latent documentation services that are changing part of the workflow.
Yeah.
But they're not making the hard parts of the workflow inherently more easy and delightful in their own way. Like it's not. And what does that mean when you have this like very deep information system? Like what's the future of that workflow? I think is going to be something that's very exciting.
Fascinating. Adam, I really appreciate the time today. This was a fascinating conversation. Good luck with all the research and really appreciate your time today.
Yeah, thanks for having me.
Thanks for listening to Neural Compass, the Jimini podcast. If today's conversation sparked something for you, follow us at Instagram, YouTube, or LinkedIn, or explore more at JiminiHealth.com. At Jimini, we're building the future of mental health care with effective, safe, AI-enabled continuous care. See you next time.